This sixth set of lecture videos is going to cover the topics of work, power, and energy. The goals for this chapter are: distinguish the common and technical definitions of work, find work done when an object is displaced, analyze how power is used and described in technical applications, find gravitational potential energy of an object relative to a reference level, find the kinetic energy of a moving object, and solve problems using the law of conservation of mechanical energy. Our first topic of discussion will be work. We will first look at a formal definition for work. Work is the product of the force being applied in the direction of motion and the displacement. The equation we will use to calculate work is W equals F times S, where W is work, F is the force applied in the direction of motion, and S is displacement. We can see from this equation that one very important idea is that in order for any work to be done, an object has to have some displacement due to the applied force. In other words, if you are applying a force to an object, but the object does not move, you are not doing any work. Let's take a look at the units we will be using for work. If work is a force times a displacement in metric or SI units, force is measured in newtons and displacement is measured in meters. This means that work is measured in Newton meters. One conversion for units that might be helpful is that 1 Newton meter is equal to 1 joule, which is represented by a capital J. If we are in English or standard units, force is measured in pounds and displacement is measured in feet, so work is measured in pound-feet or more commonly foot-pounds. It is important to note that work is a scalar because it does not have any particular direction. Therefore, when we are calculating work, we don't need to specify any direction. Let's take a look at a couple of calculations involving work. A worker pushes a 250-pound cart a distance of 50 feet by exerting a constant force of 30 pounds. How much work does the person do? First, we will write down all of the information we were given in the problem statement. The force being applied in the direction of motion is 30 pounds, not 250 pounds. Actually, when we calculate work, if we are pushing an object horizontally, the weight of the object, in this case the cart, doesn't matter because the weight force is not being applied in the direction of motion, which is horizontally. The distance the cart moves is 50 feet. We are trying to find the work W. The basic equation to calculate work is work equals the force in the direction of motion, F, times the displacement, S. Since this equation is already written in terms of work, our basic equation is also the working equation. Next, we can substitute the data we were given. Work equals 30 pounds times 50 feet. The amount of work this person does pushing the cart, therefore, is 1,500 foot-pounds. Let's look at one more quick example. The work required to lift 5 80-pound bags of fertilizer from the ground to the back of a truck is 1,580 foot-pounds. What is the height from the ground to the back of the truck? Like usual, the first thing we want to do is write down all of the information we are given. The work in this problem is 1,580 foot-pounds. In this problem, the force is being applied vertically because we are lifting the bags up, not pushing them sideways. Since the force is being applied vertically, the force we need is actually going to be the total weight force of all of the bags of fertilizer. We can find the total force applied by taking 5 bags times 80 pounds per bag. This gives us a total force of 400 pounds. We are trying to find the height or displacement S. The basic equation, just like the last example, is that work is equal to the force applied in the direction of motion times the displacement S. In this problem, we need to rearrange to solve for S. We can do this by dividing both sides by the force F. This gives us a working equation of displacement or height is equal to the work divided by the force. Next, we can substitute in our data. This leaves us with S equals 1,580 foot-pounds divided by 400 pounds. After dividing, we see the height from the ground to the back of the truck is 3.95 feet. This concludes our first video on work.